Planet Mercury. In the vast expanse of our solar system, 8 planets orbit the mighty Sun, each with its own story to tell, each with a character shaped by cosmic history and natural law. Among these planets, the smallest, swiftest, and perhaps one of the most mysterious is Mercury. This little world, often overshadowed by its brighter neighbors like Venus and Earth, holds secrets that stretch back to the birth of the solar system. Mercury is not just a planet, it is a living fossil of creation, a reminder of the fiery chaos from which our cosmic home emerged. To study Mercury is to look at the blueprint of planetary formation itself, because it has preserved aspects of the early solar system that other planets have long since lost. Mercury is the closest planet to the Sun, orbiting at an average distance of just 58 million kilometers, 36 million miles. To the naked eye from Earth, Mercury appears as a fleeting spark of light near the horizon during twilight, often difficult to spot because of the Sun's overpowering glare. Yet, despite its small size and its elusive appearance in our skies, Mercury has fascinated humans for thousands of years. From ancient astronomers who named it after their swift messenger gods, to modern scientists who have sent spacecraft to unveil its rugged face, Mercury has always been a planet of curiosity and wonder. In mythology and ancient belief systems, Mercury has carried symbolic importance. The Romans named it after Mercurius, the messenger of the gods, who was associated with speed and swiftness. The Greeks called it Hermes, and in Babylonian astronomy, it was known as Nabu, a god of wisdom and writing. Its rapid motion across the sky, sometimes appearing as a morning star before sunrise and other times as an evening star after sunset, earned it a reputation for agility and mystery. The ancients recognized that Mercury was unique. It never strayed far from the Sun, never climbed high into the night sky, and always seemed fleeting, as though it were a celestial trickster darting in and out of view. Scientifically, Mercury is a world of extremes. It is the smallest planet in our solar system, with a diameter of about 4,879 kilometers, 3,032 miles, making it even smaller than some moons, such as Jupiter's Ganymede and Saturn's Titan. Yet, what Mercury lacks in size, it makes up for in density. Mercury is one of the densest planets, second only to Earth, and much of its mass is concentrated in a massive metallic core. This core dominates the planet's structure and contributes to its weak but fascinating magnetic field, one of the great puzzles for planetary scientists. Mercury is also a planet of scorching heat and freezing cold. Being so close to the Sun, its surface temperature can soar to nearly 430 degrees Celsius, 800 degrees Fahrenheit during the day. Yet, with no thick atmosphere to retain the heat, nighttime temperatures plummet to around minus 180 degrees Celsius, minus 290 degrees Fahrenheit. This dramatic swing of over 600 degrees makes Mercury one of the most extreme environments in the solar system, a place where survival for any life, as we know it, would be impossible. For centuries, Mercury remained a mystery. Even powerful telescopes on Earth revealed only vague details of its surface, a shimmering disk with no clear features. It wasn't until the 20th century, with the arrival of space exploration, that humanity began to peel back its layers of mystery. The Mariner 10 mission in the 1970s gave us our first close-up images, revealing a cratered, moon-like world scarred by ancient impacts. Decades later, the Messenger mission transformed our understanding of Mercury, mapping its surface in detail, studying its thin exosphere, and uncovering evidence of water ice hidden in the shadows of its craters. Why study Mercury at all? Some might ask this question, given that it is small, barren, and inhospitable. The answer lies in its significance as a time capsule of planetary history. Mercury's surface and interior preserve clues to the early processes that shaped not just itself, but the Earth, Venus, Mars, and even the giant planets. Its enormous iron core, its strange surface features, and its tenuous atmosphere all point toward events that occurred over 4.5 billion years ago. To understand Mercury is to look backward in time, to piece together the story of how rocky planets form, evolve, and survive in the furnace of a young star. Mercury is not just a planet, It is a paradox, a puzzle, and a window into cosmic history. Its proximity to the sun makes it difficult to study, but also makes it uniquely important. It challenges scientists, inspires curiosity, and serves as a reminder that even the smallest worlds in our solar system hold stories of immense importance. In this script, we will journey deep into Mercury's secrets, its orbit and rotation, its structure and geology, its myths and mysteries, and its exploration by humankind. Piece by piece, we will uncover why Mercury, though often overlooked, remains one of the most fascinating planets of all. Mercury's story cannot be told without first understanding its unique and extraordinary relationship with the Sun. Being the closest planet to our star, Mercury occupies an environment that is unlike any other in the solar system. It lives on the very edge of survival, trapped between the scorching heat of solar radiation and the cold emptiness of space. Its orbit and rotation reveal a planet caught in a delicate gravitational dance, one that has shaped its history and its surface in ways both subtle and dramatic. Mercury orbits the Sun at an average distance of about 58 million kilometers, 36 million miles. To put this into perspective, it is only about one-third the distance that Earth orbits from the Sun. This closeness makes Mercury the fastest planet in the solar system. Racing around the Sun at an average speed of nearly 47 kilometers per second, 29 miles per second, Mercury completes a single orbit in just 88 Earth days. This rapid orbital speed is the reason ancient observers associated it with swiftness, naming it after the messenger gods who are believed to move with extraordinary agility. But Mercury's orbit is not just fast, it is also unusually shaped. Unlike Earth, which travels in a nearly circular path around the Sun, Mercury follows an elliptical orbit, meaning it is more stretched out. At its closest point to the Sun, known as perihelion, Mercury comes within about 46 million kilometers, 29 million miles, of the Sun. At its farthest point, called aphelion, it lies about 70 million kilometers, 43 million miles, away. This large difference between perihelion and aphelion makes Mercury's orbit the most eccentric, oval-shaped, of all the planets in the solar system. This eccentric orbit has profound consequences for Mercury's climate and conditions. When it is at perihelion, Mercury experiences its most intense solar heating, with sunlight more than 10 times stronger than what we receive on Earth. The Sun looms more than 3 times larger in Mercury's sky than it does in ours, dominating the heavens in a way that is difficult to even imagine from Earth. For any observer on Mercury's surface, the Sun would appear not only overwhelming in size but also in brightness, an eternal fireball that commands every aspect of life and environment on this tiny planet. Yet, as fascinating as Mercury's orbit is, its rotation is even stranger. For centuries, astronomers struggled to determine how Mercury spins on its axis. Early observations led many to believe that Mercury was tidally locked to the Sun, meaning that one side of the planet always faced the Sun while the other remained in eternal darkness, just as the Moon always shows one face to Earth. This belief persisted for much of the 19th and early 20th centuries. However, radar studies in 1965 revealed the surprising truth. Mercury rotates, but in a most unusual way. Mercury's rotation is locked in what scientists call a 3:2 spin, orbit resonance. This means that Mercury rotates 3 times on its axis for every 2 orbits around the Sun. In practical terms, this gives Mercury a day, sunrise to sunrise, that lasts about 176 Earth days, which is actually longer than its year of 88 Earth days. Imagine standing on Mercury's surface. You would witness the Sun rising slowly above the horizon, moving gradually across the sky, and then, in a bizarre twist caused by the eccentric orbit, the Sun would appear to reverse its path for a while before continuing forward again. A single day on Mercury would feel eternal, filled with scorching heat and long, drawn-out hours of sunlight, followed by equally long stretches of freezing darkness. This strange resonance between orbit and rotation is not an accident. It is the result of billions of years of gravitational interactions between Mercury and the Sun. The Sun's immense gravitational pull has shaped Mercury's spin into this delicate balance, a compromise between tidal forces and the planet's own inertia. The result is a planet with a rhythm that is unlike any other in the solar system, a world where time itself seems distorted by cosmic forces. The eccentricity of Mercury's orbit also plays a role in one of the most important scientific discoveries in modern physics, the theory of general relativity. For centuries, astronomers noticed that Mercury's orbit did not behave exactly as Newton's laws predicted. Specifically, its perihelion, the point of closest approach to the Sun, advanced slightly more than expected with each orbit. The discrepancy was small, but it could not be explained by the gravitational influence of other planets alone. For decades, scientists puzzled over this mystery, even proposing the existence of another hidden planet, nicknamed Vulcan, orbiting closer to the Sun to account for the anomaly. It was not until Albert Einstein introduced his theory of general relativity in 1915 that the riddle was solved. According to relativity, massive objects like the Sun curve the very fabric of space-time around them. Mercury, being so close to the Sun, travels through this curved space-time, causing its orbit to shift slightly with each revolution. The prediction matched perfectly with the observed precession of Mercury's orbit, providing one of the first confirmations of Einstein's groundbreaking theory. Thus, Mercury is not only important as a planet in its own right but also as a cornerstone in the history of science, helping humanity unlock the mysteries of gravity and the nature of the universe. In addition to its scientific importance, Mercury's orbit and rotation create a landscape of extremes on its surface. The long, slow days mean that when the Sun rises, it beats down on the land for weeks at a time, heating the rocks to blistering temperatures. When the Sun finally sets, the surface is left to freeze in the darkness for equally long stretches. This cycle of heat and cold has fractured Mercury's crust, leaving scars and cracks that tell the story of its struggle against the relentless forces of its environment. Mercury's closeness to the Sun also makes it difficult to observe from Earth. The planet never strays more than 28 degrees from the Sun in our sky, meaning it can only be seen just after sunset or just before sunrise. For stargazers, this makes Mercury a fleeting jewel, often appearing as a faint, low on the horizon, shimmering in the Sun's glare. Ancient astronomers were puzzled by this behavior, sometimes mistaking Mercury's morning and evening appearances for two different celestial objects. It was only after careful observation that they realized they were seeing the same planet at different times. Through its orbit and rotation, Mercury demonstrates the complex interplay between gravity, motion, and cosmic history. It is a world shaped by the Sun's overwhelming presence, a planet caught in a unique rhythm of time and space. Its orbital eccentricity not only challenges our understanding of celestial mechanics, but also provided the key to unlocking the deepest truths of modern physics. In studying Mercury's dance around the Sun, we do not just learn about a planet, we glimpse the fundamental rules that govern the universe. When spacecraft first flew past Mercury, the images they sent back astonished scientists. The surface that unfolded before human eyes was both familiar and alien. It looked, at first glance, strikingly similar to Earth's moon, a barren landscape, pockmarked with countless craters, ridges, and plains. But as the details emerged, scientists realized that Mercury's surface is far more than a lunar twin. It is a unique geological record of the solar system's violent beginnings and Mercury's own dramatic history. Mercury's surface is scarred by impact craters, reminders of the chaotic early era of planetary formation. Over 4 billion years ago, the young solar system was a dangerous place. Planetesimals, rocky fragments, and debris left over from planetary formation were constantly colliding with growing planets. Mercury, being small and close to the Sun, endured one of the heaviest bombardments in the solar system. Unlike Earth, which has erased many of its craters through erosion, volcanic activity, and plate tectonics, Mercury has preserved its scars. With no thick atmosphere to shield it and no active weather systems to erode its features, the craters remain frozen in time, silent witnesses to a violent past. One of the most prominent features on Mercury's surface is the Calorus Basin, a massive impact structure stretching about 1,550 kilometers 960 miles, across. This colossal basin was formed when a giant asteroid or comet slammed into Mercury around 3.9 billion years ago, releasing unimaginable amounts of energy. The impact created a ring of mountains surrounding the basin and left behind smooth plains of volcanic material that filled the crater's interior. To put its size into perspective, the Caloris Basin is so vast that it could cover nearly a quarter of the continental United States. The violence of its creation is a reminder of the destructive forces that shaped the early solar system. The Caloris Basin is not only remarkable for its size but also for the strange geological effects it produced on the opposite side of the planet. Directly opposite the basin lies a region of jumbled, chaotic terrain known as the Weird Terrain. Scientists believe that the seismic shockwaves from the Caloris impact traveled through Mercury's interior and converged on the opposite side, fracturing the crust and leaving behind a tortured landscape of ridges, hills, and valleys. This strange echo of the impact stands as a powerful testament to the interconnectedness of a planet's geology, how an event on one side can shape the features on the other. Beyond the craters and basins, Mercury's surface reveals evidence of ancient volcanic activity. Smooth plains found in many regions are not just the result of impacts, but also of lava flows that once spread across the surface, filling low-lying areas and covering older craters. These plains suggest that Mercury was geologically active in its past, with molten material rising from its interior to reshape the land. Unlike Earth, Mercury does not have active volcanoes today, but the traces of this volcanic past provide clues about its internal structure and thermal evolution. Another striking feature of Mercury's landscape is the presence of lobate scarps, long, curved cliffs that stretch for hundreds of kilometers across the surface. These scarps were formed as Mercury's core cooled and contracted over billions of years, causing the crust to wrinkle and buckle like the skin of a drying fruit. Some of these cliffs rise more than a kilometer high, cutting across craters and plains alike, showing that they formed relatively late in Mercury's geological history. These scarps are among the strongest pieces of evidence that Mercury is a shrinking planet, still slowly contracting even today. The surface of Mercury also holds a fascinating secret: the presence of hollows. These are irregular, shallow depressions that appear bright and fresh compared to their surroundings. Unlike craters, which are formed by impacts, hollows seem to be caused by the loss of volatile materials from Mercury's crust, possibly through processes like sublimation or space weathering. The hollows are mysterious because they suggest that Mercury's surface contains materials that are more volatile than scientists once expected for a planet so close to the Sun. Their discovery challenged earlier assumptions and opened new questions about Mercury's composition and history. Mercury's landscape is further shaped by the relentless process of space weathering. Without a protective atmosphere, its surface is constantly bombarded by micrometeorites and exposed to the full force of the solar wind, a stream of charged particles flowing outward from the Sun. Over time, these processes darken and alter the surface material, giving Mercury its gray, dusky appearance. Yet, within this monotone landscape are subtle variations. Some regions appear brighter, especially around young craters where fresh material has been exposed. These brighter areas, called bright rays, radiate outward from impact sites like cosmic fingerprints of recent events. Despite its barren appearance, Mercury's surface is not completely lifeless in terms of activity. The planet experiences thermal stresses that fracture rocks and boulders due to the extreme temperature swings between day and night. During the blistering daytime heat, surface materials expand, only to contract violently during the freezing nights. Over millions of years, this thermal cycling breaks rocks into fragments and shapes the regolith, or layer of loose material, that blankets the planet. Mercury's geology also tells a deeper story about its formation. One of the great mysteries is why Mercury has such a disproportionately large iron core, making up about 85% of its radius. One theory suggests that Mercury may have once been larger, with a thick mantle and crust similar to Earth. A colossal impact early in its history might have stripped away much of its outer layers, leaving behind a dense, metal-rich planet. Another theory proposes that intense solar radiation in the early solar system may have prevented Mercury from retaining lighter materials, leading to its unusual composition. Whichever scenario is true, Mercury's surface is a direct reflection of this violent and selective history. For planetary scientists, the surface of Mercury is like a library of geological records. Each crater, each ridge, each basin is a page in the story of the solar system's evolution. Unlike Earth, where tectonics and erosion constantly rewrite the landscape, Mercury has preserved its ancient features with remarkable clarity. It offers scientists a rare opportunity to study a planet that still carries the scars of the solar system's infancy, relatively untouched by the processes that have reshaped other worlds. For a human observer standing on Mercury, the view would be both breathtaking and unsettling. The horizon would stretch across a rocky, desolate plain, punctuated by towering cliffs and crater rims. Above, the sun would dominate the sky, appearing more than twice as large as it does on Earth, blazing with an intensity that would be nearly unbearable. At night, the stars would shine brilliantly against the black sky, unfiltered by atmosphere, while the ground beneath would radiate the freezing cold of space. It would be a place of silence, of extremes, a world that speaks not through life and activity, but through the silent testimony of stone. Mercury's surface is not just a barren wasteland. It is a canvas painted by cosmic forces, impacts, volcanism, contraction, and space weathering. It is both a record of destruction and a testament to resilience, a world that has endured the full fury of its environment and still carries the marks of its survival. To study Mercury's geology is to look directly into the heart of planetary science, to see how worlds are shaped, scarred, and transformed over billions of years. At first glance, one might assume that Mercury, being a planet, must have an atmosphere of some kind, perhaps thin, but at least present in some measurable form. Yet, in reality, Mercury's atmosphere is almost non-existent. Instead, what Mercury possesses is something much more fragile and tenuous, an exosphere. This difference is critical, for it explains not only why Mercury is a world of such extremes, but also why it has remained largely unchanged for billions of years. An atmosphere, like Earth's or Venus's, is a thick layer of gases held to a planet by gravity. It provides weather, shields the surface from radiation, and redistributes heat across the globe. An exosphere, however, is an ultra-thin collection of particles so sparse that they rarely collide with one another. Mercury's exosphere is more like a temporary veil than a permanent blanket. Its atoms and molecules are constantly being replenished and just as quickly swept away by the forces of space. So, why does Mercury lack a substantial atmosphere? The answer lies in its size and proximity to the Sun. Being the smallest planet in the solar system, Mercury has relatively weak gravity, insufficient to hold onto light gases like hydrogen, helium, or water vapor. And being so close to the Sun, the planet is constantly bombarded by solar radiation and the solar wind, a steady stream of charged particles. These forces strip away any gases that might linger near the surface, leaving Mercury virtually naked against the vacuum of space. Yet, Mercury's exosphere is not empty. It contains trace amounts of elements like oxygen, sodium, hydrogen, helium, potassium, and calcium. These are not present in quantities that could support weather or pressure, but exist as a thin, constantly shifting envelope. Scientists have discovered that many of these elements are released through processes such as solar wind sputtering. High-energy particles from the sun strike Mercury's surface, knocking atoms loose and sending them into space. Micrometeorite impacts. Tiny meteoroids constantly strike the planet, vaporizing small amounts of surface material that then escape into the exosphere. Thermal desorption. The intense daytime heat causes atoms from the surface to boil off, temporarily floating above the planet before drifting into space. Among the most fascinating features of Mercury's exosphere are the glowing sodium tails observed by astronomers. Just as comets produce tails when solar radiation pushes material away, Mercury develops a faint, comet-like tail of sodium atoms that streams into space behind it. This tail is invisible to the naked eye, but detectable with specialized instruments, and it serves as a reminder that Mercury, despite being a planet, shares some strange similarities with comets. The lack of atmosphere has another consequence. Mercury experiences some of the most extreme temperature variations of any planet in the solar system. During the long daytime hours, when sunlight beats down relentlessly on the surface, temperatures soar to around 430 degrees Celsius, 800 degrees Fahrenheit. This is hot enough to melt lead and makes Mercury one of the hottest worlds in our solar system. Yet, as the sun sets and the planet's surface is plunged into darkness for weeks at a time, the absence of an atmosphere to trap heat allows temperatures to drop drastically, plummeting to nearly minus 180 degrees Celsius, minus 290 degrees Fahrenheit. This enormous swing of more than 600 degrees between day and night creates an environment of constant stress on Mercury's crust. Rocks expand and contract with the heat, leading to cracks and fractures over time. It also makes Mercury a planet of extremes, burning deserts by day, frozen wastelands by night, a world in which the concept of climate becomes meaningless because the surface conditions are dictated entirely by exposure to the sun. Despite these extremes, one of the most surprising discoveries about Mercury is the presence of water ice. At first, this seems impossible. How could ice exist on a planet so close to the sun, where daytime temperatures can reach such blistering levels? The answer lies in Mercury's polar craters. Near the poles, certain craters are so deep and their walls so steep that sunlight never reaches the bottom. These areas, called permanently shadowed regions, remain in eternal darkness, shielding them from the sun's heat. Within these frozen traps, scientists have detected bright deposits that radar studies and spacecraft data confirm are water ice, likely mixed with organic compounds. The existence of ice on Mercury is not only surprising but also profoundly important. It suggests that volatile materials like water were delivered to Mercury, perhaps by comets or asteroids, and that despite its harsh conditions, the planet has managed to preserve them in hidden sanctuaries. This discovery adds another layer to Mercury's story, showing that even the most unlikely worlds can harbor ingredients that are vital for understanding the chemistry of life and planetary evolution. Without a protective atmosphere, Mercury is also exposed to the full intensity of cosmic radiation and the solar wind. This environment is incredibly hostile, bathing the surface in high-energy particles that continually alter its chemistry. Over time, this bombardment creates a process known as space weathering, which darkens and modifies the minerals on Mercury's surface. Unlike Earth, where the atmosphere and magnetic field shield us from these dangers, Mercury stands defenseless, enduring the sun's fury in its rawest form. Another fascinating effect of Mercury's thin exosphere and lack of atmospheric scattering is the view of the sky from its surface. On Earth, our atmosphere scatters sunlight, creating a bright blue sky during the day. On Mercury, the sky would remain black even under the blazing sun because there are no atmospheric particles to scatter the light. The sun would dominate the heavens, appearing more than twice as large as it does from Earth, its light glaring against the pitch-black backdrop of space. At night, the stars would shine with brilliant clarity, unblurred by air or weather, but the freezing surface beneath would make it a silent, lifeless panorama. Taken together, Mercury's exosphere and climate extremes paint a picture of a planet that is both simple and complex. On the one hand, it is barren, without winds, clouds, or weather patterns. It lacks the dynamic systems that make Earth or even Mars so visually rich. On the other hand, its very emptiness reveals truths about planetary science that cannot be learned elsewhere. It shows us what happens to a rocky planet stripped bare, exposed to the sun's unrelenting power, and it challenges our assumptions about where water and volatile compounds can exist. Mercury's exosphere may be thin, but it is not meaningless. It is a fragile, transient atmosphere that constantly interacts with the surface and the solar environment. It reminds us that even the smallest details, the release of atoms by micrometeorites, the faint glow of sodium tails, the preservation of ice in shadowed craters, are significant in the grand scheme of planetary science. By studying Mercury's atmosphere, or lack thereof, scientists gain a deeper understanding of how planets evolve, how they lose or retain volatile materials, and how their proximity to their star shapes their destiny. In this way, Mercury teaches us a profound lesson. Not all worlds need to be bustling with storms or weather systems to be scientifically important. Sometimes, silence and emptiness are just as revealing, carrying within them the keys to cosmic history. While Mercury's surface tells a dramatic story of impacts, volcanism, and contraction, the planet's true uniqueness lies hidden beneath its crust. For a world so small, Mercury has an interior structure that is surprisingly complex and puzzling. Its dense composition, enormous core, and unexpected magnetic field have forced scientists to reconsider what they thought they knew about the formation of rocky planets. In many ways, Mercury is less a planet of the present and more a fossil from the dawn of the solar system, preserving clues about processes that no longer occur on other worlds. At its most basic, Mercury is composed of three main layers: a crust, a mantle, and a core. Yet, the proportions of these layers are unlike anything seen on other planets. Mercury's core is enormous, making up about 85% of the planet's radius and accounting for the majority of its mass. This means that, in terms of structure, Mercury is essentially a giant metallic ball wrapped in a thin shell of rock. For comparison, Earth's core makes up only about 55% of its radius. This unusual dominance of metal over rock makes Mercury the densest planet in the solar system once its size is taken into account. But why does Mercury have such a massive core? This question has been at the heart of planetary science for decades. Several theories attempt to explain it. The giant impact hypothesis. One of the most widely accepted ideas is that Mercury was once much larger, with a thick silicate mantle and crust similar to Earth's. At some point early in its history, a colossal impact with another planetary body stripped away much of Mercury's outer layers, leaving behind the dense metallic core and a thin rocky shell. This catastrophic collision would explain both the core's unusual size and the planet's overall composition. Solar nebula hypothesis. Another theory suggests that Mercury formed in the extreme heat of the early solar system. In this scenario, lighter elements and minerals were vaporized and carried away by intense solar radiation, leaving behind a planet composed primarily of heavier metallic elements. If this is true, Mercury may represent a unique class of planet shaped directly by its proximity to the newborn sun. Multiple smaller impacts. A third possibility is that Mercury did not lose its mantle in a single event, but rather through a series of smaller collisions that gradually eroded its outer layers over time. This would paint Mercury not as a victim of one catastrophic event, but as a survivor of repeated cosmic violence. Regardless of how Mercury ended up with such a massive core, its internal structure is still revealing surprises. Data from NASA's Messenger spacecraft showed that Mercury's core is not entirely solid. Instead, it is at least partially liquid, surrounded by a solid outer shell and possibly even containing layers of different compositions. This partially molten core is critical for understanding one of Mercury's greatest mysteries, its magnetic field. For decades, scientists assumed that Mercury would be too small and too geologically inactive to generate a magnetic field. After all, Mars, larger than Mercury, lost its magnetic field billions of years ago. Yet, when the Mariner 10 spacecraft flew past Mercury in the 1970s, it made a shocking discovery. Mercury has a global magnetic field, though weaker than Earth's. This unexpected finding changed everything we thought we knew about planetary magnetism. Mercury's magnetic field is about 1% as strong as Earth's, but its very existence suggests that the planet still has an active dynamo, a process in which the movement of molten metal in the core generates magnetic fields. For such a small planet to still maintain a liquid, churning core is astonishing, and it raises profound questions about how Mercury retains enough internal heat to keep the dynamo alive. Some scientists speculate that radioactive decay within the core provides a steady supply of heat, while others suggest that the unique chemistry of Mercury's interior allows its core to remain partially molten longer than expected. Even stranger is the shape of Mercury's magnetic field. Unlike Earth's field, which is relatively centered around the planet's core, Mercury's field is offset, shifted northward by several hundred kilometers. This asymmetry means that the magnetic environment of Mercury is lopsided, with stronger interactions occurring in the northern hemisphere than in the southern. Such an imbalance defies easy explanation and has challenged models of how dynamos work in planetary interiors. The magnetic field also interacts directly with the solar wind, creating a miniature version of Earth's magnetosphere. However, because Mercury's field is much weaker, it does not provide the same level of protection. Instead, solar wind particles frequently penetrate close to the surface, stripping away atoms and contributing to the formation of Mercury's exosphere. In this way, Mercury's magnetic field is both a shield and a doorway, guiding particles into regions where they continually reshape the planet's environment. Another geological mystery tied to Mercury's interior is its global contraction. As its massive core cooled over billions of years, the planet shrank by as much as 7 kilometers for miles in radius. This shrinkage created the lobate scarps that scar the surface, some stretching for hundreds of kilometers. Unlike Earth, which has plate tectonics to release internal stress, Mercury's rigid crust responded by wrinkling and cracking. These scarps are still visible today, suggesting that Mercury's interior continues to cool and contract. In fact, some evidence suggests that Mercury may still be tectonically active in small ways, with fresh scarps forming in relatively recent geological timescales. Mercury's interior composition also raises questions about the distribution of lighter elements like sulfur. Surprisingly, messenger data revealed that Mercury's surface is enriched in volatile substances that should have evaporated away if the planet had formed so close to the Sun. This discovery contradicts earlier assumptions that Mercury's proximity to the Sun stripped it of volatile materials. Instead, it appears Mercury may have retained more of these elements than expected, complicating theories about its formation and evolution. One of the more speculative but fascinating aspects of Mercury's interior is its potential to provide insights into exoplanets. Astronomers have discovered many rocky planets orbiting other stars, some much larger and denser than Earth. By studying Mercury's oversized core and unusual geology, scientists can make predictions about how these exoplanets might have formed and how their internal dynamics could work. In this sense, Mercury is not just a planet of our solar system, it is a laboratory for understanding planets everywhere. In summary, Mercury's interior is a paradox, a tiny world with a giant core, a planet expected to be geologically dead yet still maintaining a magnetic field, a rocky body that seems simple on the surface, but is extraordinarily complex within. Its geological mysteries, from the cause of its massive core to the persistence of its dynamo, remain among the most compelling questions in planetary science. By probing the secrets beneath Mercury's crust, we come closer to answering fundamental questions not only about Mercury itself, but also about the processes that shaped Earth and the other terrestrial planets. Mercury reminds us that size is not destiny. Despite being the smallest planet, it carries within it some of the biggest puzzles of the solar system. Its interior is a story of survival, resilience, and mystery, a molten heart that continues to beat long after many expected it to fall silent. Mercury, the smallest and swiftest planet, proves that size does not limit significance. From its blistering dayside heat to its frozen polar shadows, it embodies contrasts that defy expectation. Its oversized core, fragile exosphere, and surprising magnetic field remind us that the universe is full of paradoxes, answers that only raise deeper questions. For centuries, Mercury was a distant enigma, glimpsed fleetingly in the dawn and twilight skies. To ancient civilizations, it was a messenger of the gods, a wandering light too elusive to fully grasp. Today, with the help of spacecraft like Mariner 10 and Messenger, and soon Bepicolombo, humanity has peeled back layers of mystery. Yet, even with these missions, Mercury has not surrendered all its secrets. Instead, it stands as a challenge, urging us to look deeper, to ask sharper questions, and to test the limits of our knowledge. Mercury is not simply a planet, it is a time capsule of the solar system's birth. Locked within its dense metallic core and scarred surface are records of collisions, contractions, and cosmic forces that shaped not only Mercury, but the Earth itself. To understand Mercury is to understand our origins, the processes that forged the terrestrial planets, and the balance of destruction and creation that governs the universe. Looking forward, Mercury offers more than answers about the past. Its study helps us prepare for the future, especially as astronomers discover rocky exoplanets orbiting close to their stars. By learning how Mercury endures extremes of heat, radiation, and solar wind, we gain insight into the conditions that shape countless other worlds beyond our solar system. In this sense, Mercury is not just a neighbor, it is a guide. And so, Mercury endures, scarred, battered, shrinking, but never silent. It whispers the story of cosmic beginnings, of survival against odds, of mysteries yet unsolved. The planet nearest the Sun is also one of the deepest teachers in the night sky, reminding us that even the smallest worlds can hold the grandest truths. The story of Mercury is not finished. It is still being written in the labs of scientists, in the orbits of spacecraft, and in the curious eyes of every person who wonders at the night sky. Each discovery brings us closer, but each answer expands the horizon of mystery. In Mercury, we find the eternal truth of science, that the universe is never exhausted and the quest to understand it is endless. Mercury, the swift messenger of the heavens, continues to speak. The question is, are we listening?